Well, hello again. It's been a while. It's me, Vivian, the crazy and unorganized. And I have actually released a new video for once. Keep watching if you want to see why I've been gone for so long. I'm going to go over that at the end. That way, people who are just coming to the channel for the first time can watch the video and enjoy it. Anyways, in this video, I'm going to be testing a way to make an LED bulb dimmer. I'm starting a project using an old dashboard gauge cluster from my car, and I'm going to be replacing like lights and LEDs and crap on it. So I found that in replacing some of those bulbs, they were just too bright for my liking, and they just kind of blinded me at night and I didn't like it. So I'm going to be experimenting in this video with different resistance values to try to find one that works best for the LED bulbs that I have available. Why, hello there. I am about to do some work dimming this LED bulb over here. It's a little, it's called either a T5 or a 74 automotive LED. This guy is meant to be a replacement for this little incandescent bulb right here. And I'll show you in a minute, but this guy is significantly brighter than this guy. So the first thing that I'm going to do in this testing process, and this may or may not be destructive, so these both are sacrificial. I'm willing to lose them. The first thing, though, that I am going to do is I'm going to solder leads onto these small little, if I can get it to focus, onto these little pads right here. And then you may or may not just be able to see, but there are a couple of metal leads sticking off of this incandescent bulb. So I'm going to solder those up and then plug it into the breadboard that you see right here. Also, sorry in advance for my somewhat janky setup. I am a bit eclectic like that. Anyways, the idea is to put a variable resistor or a potentiometer in parallel with this small little surface mount resistor that you see right here. I don't know if the camera will pick it up because I seem to have trouble focusing today. There we go. So it says 121 on it. It's upside down. Here we go. So it says 121 on it. And the 1-2 denotes the significant figures of it. So that basically means that it's 1-2 with a certain number of zeros after it or before it. And in this case, that 1 at the very end denotes the number of zeros after the two significant figures. So all that is to say, in a very complicated and roundabout way, that there is a 120 ohm resistor that is limiting the current going through this little 3-diode array. So let me go solder that together and then show you the process that I'm going to use to test it and make it a little bit dimmer for my dashboard. Okay, so here's what I've come up with so far. On this little guy, if I can again get it to focus or maybe get some better light on it. I've got two little leads attached to either end of the resistor, and that is so that I can connect another resistor in parallel to it. And then I've got a couple of leads connected to either side of it. I've done some experimenting with how to actually power this thing up, and it appears that on the other side you need to bridge these two guys for the, I believe this is the negative terminal, so ground, and then over here, the positive terminal, it just goes to one side of the resistor for the 12 volts. So what I'm going to do next is I'm going to set this guy up on my breadboard along with this guy. I ended up not being able to solder extra wires onto it, but I just kind of pulled the wires that were already present downwards a little bit so it'll actually fit on the breadboard. So hopefully it connects. We'll see. But yeah, so I'm going to use this potentiometer and just get everything hooked up so you can hopefully see that process. Okay, so I've got everything set up over here. So as I turn this potentiometer upwards, the resistance will increase. And as I turn it downwards, I guess it would be clockwise for up, counterclockwise for down, that should increase the amount of resistance in parallel with this little LED over here. I've got power and ground hooked up to both the incandescent bulb and the LED bulb. And I'm going to just crank up the voltage a little bit to 12 volts because this is going in a car. Automotive typically is 12 volts. Also going to crank up the current to 220 milliamps just because I don't know actually how much this will take. So I know that both are kind of able to limit the amount of current going in. So hopefully I don't blow anything up. I'm sure that this will be relatively safe though. And I'm not seeing any signs of life from either bulb. Maybe if I just take out this guy. Nope. What about if I just take out this guy? Nope. So what I'm seeing when I turn on the power supply, voltage goes down all the way, current maxes out. So that tells me that there's probably a short somewhere. So time to find that. All right, I'm back again and I've acquired more knowledge. So I ended up fixing the issue. On the LED, those two pins that were bridged that I said I experimentally figured out, I must have just done a bad job experimentally figuring it out because unbridging them was actually the key to getting it to work again. And this incandescent bulb burned out. So probably I would assume that's because this guy just drew a bunch of current and then knocked that guy out. So with all that fixed, I can show you what it looks like. I'm going to remove this guy. I'll explain in a moment why. You can see they're both very bright. However, I think the LEDs may be making the incandescent one look dull by comparison. So by itself, you know, it's bright. It's good for an automotive application, this incandescent bulb. But in comparison to the LED, which I will show you now, it's significantly less bright, which in this specific situation is not a good thing because it's blinding me when I drive at night. Hence this whole video. Okay, so you can see the LED, ridiculously bright, draws about 27, 26 milliamps. Oh, and I also forgot to mention, too, that the incandescent bulb draws, there we go, about 94 milliamps. So, let's put them together, see what happens. Okay, so both together draws 118 milliamps, which makes sense. You know, you add those two numbers, 94 and 126 together, you get about 120 milliamps, and that's what we're seeing with both of them running together. However, this guy, and I'll explain mathematically how this works in a minute, when I add it in parallel to this LED, suddenly, oh, let's turn it all the way down. There we go. Suddenly it gets brighter and you can see that the current draw is going way up. So if I just turn it up a tiny bit, you can see it drops back down, and on the screen, as it rises higher, the potentiometer resistance rises. The current draw drops down to what we'd expect at 121 milliamps. So that tells me that running this guy in parallel with the resistor on the LED board is not a great idea. So what I'm going to do is remove the resistor from this LED and then just directly run this as the new resistor. So more soldering. Okay, so as promised, here's why the behavior that we saw with the parallel resistor looked the way that it did. So it turns out there's actually a formula, and I hope that you'll pardon my using Microsoft Paint. It's just easy to use. So there's actually a formula for calculating resistance in parallel circuits as long as you have kind of nothing but resistors. And it looks something like this. So 1 over R total equals 1 over R1 plus 1 over R2. And I guess just to clarify a little bit more what I mean by a parallel circuit, so there's sort of two types, or I guess three types of resistor circuits. There's series, parallel, and sort of a combination of the two. I won't go over the combination, but I will go over the series and parallel versions. So let's say in this series circuit, we have two resistors, R1 and R2. You can see that your voltage, this is using conventional current. I know that like electrons technically move from areas of negative charge to areas of positive charge. Don't at me. But just sort of for the sake of simplicity, using conventional current, we'll say that your electrical current is moving through R1, and then it moves through R2 to the ground. And so if we want to know the resistance of this particular circuit, we would say that the total resistance is R1 plus R2. However, that is not the circuit that I'm working on. The circuit that I'm working on looks more like this. So here's R1, and here is R2. So as opposed to them being connected directly, they're both kind of connected to both ends of the circuit. And so this formula over here actually explains this behavior. And we can actually use some algebra to make this equation a little bit clearer, because it's like, what does this even mean, right? So this formula is something called product over sum. And what it looks like is R total equals R1 times R2 over R1 plus R2. And the way that we get this, I won't actually go into the derivation. It's pretty simple though. It's you basically find the common denominator of R1 and R2, and then you solve for R total using the previous like 1 over R total equals 1 over R1 plus 1 over R2. Like I said, I won't bog you down in the details too much, but what this guy allows us to do is it allows us to kind of intuitively analyze what happens to R2 as we change our circuit. So if you'll remember, I had a potentiometer. So I could basically change the value in it from essentially 0 ohms all the way to about 10K. And for the sake of argument, so nothing really has like zero resistance. Like you have superconductors that have very, very low resistance, but it still has some resistance. However, in this circuit, we'll just maybe call it 1 ohm for practicality's sake. I mean, that was about the lowest thing that I was reading in it. So let's say that R2 is just a really low value. Now, what's going to happen to R total as a result of this? Well, it turns out that R2, being a small value on the top, is going to cause R1 to also be a pretty small value, and the denominator to kind of remain the same. So what it ends up happening is that R total actually decreases overall. Now, let's look at Ohm's law, which kind of describes in DC circuits, which this is, the behavior of voltage in response to current and resistance. So if we're, this is like your typical Ohm's law that you'd see in a textbook, but we can also rewrite it a little bit, just algebraically speaking, as V over R equals I. And what this means is that the amount of current that we'll actually see in a circuit, that being this I figure, is this ratio of voltage to resistance. And we have we've established, mathematically speaking, earlier that our total resistance in this parallel circuit, when R2 is low, is decreasing. So let's just say that R, this R is the same thing as R total, and that it's like a lower value than 121 ohms. So if we have V over 121 ohms, that is, some current value that's going to be allowed through the circuit. However, if we have the same voltage over a lower resistance, that's going to be a much higher current. So this is going to allow in much more current, which means LED brighter. LED have more light coming out of it now. So yeah, hopefully that made some sense. I hate to have like a prerequisite of, Math 101 for this video, but, for those interested, here's the math. And for those not interested, I'll put some kind of timestamp in the video. But yeah, anyways, thank you. Be kind of nice to be able to film this process, because removing surface mount parts is something that many people struggle with, and I can understand why. I've soldered for many years at this point, and so it's pretty simple for me at this point in my life to be able to do. But yeah, what I find works best is getting quite a bit of solder on your iron, and then trying to heat up both contacts at the same time, and then just use the surface tension of the solder to remove your surface mount part. This guy's being a little stubborn. Also hoping I don't burn the LED in this process, because LEDs like to burn up ridiculously easy. Okay, so boop. I got one of the sides to lift up, and that's it off. Maybe if I use something that wasn't the actual solder wire, it'd be easier to remove this. There we go. Okay. There's that surface mount part removed. This is one of the drawbacks of using my phone. So yeah, there's that off. I am going to now solder on each of these wires. One to each of the pads. So that's one. Okay, there's both of them. I'm also going to take care to make sure that I actually start up using this LED, not at 0 ohms because that could burn out the LEDs. So let's hook this up and try it again. Okay, so now what I've done is I've actually attached 2 more wires to either end of my multimeter, measuring resistance, and they are on either end of this little pot. So we can see right now, pretty low reading, 8.2 ohms, 7.1 now that I moved it slightly, and it's kind of all over the place, but it's generally pretty low. Now as I turn it up, you can see it's going up quite quickly. I think this is what's called a logarithmic taper, because it is increasing at a more logarithmic way, which is to say exponential. So I'm going to try my best to maybe get this around 120 ohms. We'll see how successful I am in that. And you can see just how fast it changes. At that logarithmic curve, it just, yeah. Okay, so 124 ohms. I'm happy with that. So what we would expect to see is this LED to light up about as bright as it did earlier with the surface mount resistor on it. And we can see that that is about the case. We're still getting about 121 milliamps. And we can also see that the resistance has changed through the multimeter. So turning this back off, I'm going to change these parameters a little bit. Maybe try to hit like, I don't know, 250 ohms. What I'm trying to do now is I'm trying to get these guys to be roughly the same brightness. So I don't really know what value that's going to be, and hence this experimental setup. So I guess we'll find out. Okay, they're definitely a little closer, but I think we can still go a little bit more dim. So I'm going to try maybe, yeah, 550 ohms. That works for me. It says 0.55 kiloohms, so same difference. Okay, yet less bright, even closer in terms of brightness. Great. Let's try 1K. That'd be a nice round value to go to. Okay, 1.0506. Okay, still getting more dim. One thing that I'm curious about too is what would happen if I go up all the way. So if I go up to 9.5 ohms, or 9,500 ohms, 9.5 kiloohms, and then try this, there doesn't seem to be like a ton of difference, but there is, I mean, they're pretty close in brightness. I don't know, I might call it there. I mean, we're only drawing 3 milliamps from the LED. It's a nice clear white. That could work. Yeah, you know, I think I'm happy with that. I'm going to call it here and say that 10K going to work just fine. Hello, it's me again. So back to why I've been absent from YouTube for so long. I do appreciate, and I have read all the comments that are saying, you know, like, why don't you come back? Why don't you make more videos? And I have wanted to for a long time. The truth is, I was at a very interesting point in my life when I was originally making videos on this channel. So I, at the time, was not employed, and, you know, was kind of going through a transitional period, going back to school, and just dealing with a lot in my life at the time. So I come back to you now, having more projects, realizing, wait, I can actually just film the stuff that I'm doing and post it to YouTube, and people would probably enjoy it. And I just kind of finally have the wherewithal to do it. And I'm also at a similar point in my life. I have worked somewhere new for the last 3 years, recently got laid off because of the economy. It's just, you know, the market segment that I was working in took a little bit of a downturn. And it was coming for about a year. So, yeah, I find myself still being in school. Almost got my associates in engineering, so hopefully that'll come soon. And, yeah, just been kind of quietly doing my thing. So, hopefully I can post more videos as I have more stuff in development for different projects and stuff. I am currently working on some weird stuff. I'd like to tear open the NESs again. I actually started filming that project, and I just found that I got really mired down in details. Being like, oh yeah, I'm wearing this special soldering lab coat that I wore at, my previous job. Yeah, so it got really bogged down in details. It got really long for no reason, me explaining everything. And honestly, I'm the kind of person where I would prefer to just have the jankiest lab setup like you would have seen in this video, where it's like on the floor next to my soldering iron and a power supply and a breadboard, and I'm just doing stuff. That's kind of what I prefer, kind of free spirited. I also don't really have like a dedicated workspace. I'm kind of cramped for space at the moment. Don't like have a workshop. I had to move back in with my parents after I lost my previous job when I was unemployed. When I started making YouTube videos, I was, renting a room in a house. So yeah, that's why you've probably noticed that the scenery has changed around me. Yeah. Obviously working back towards my goals, moving back out, getting a, better job, better paying, especially in this economy because, oof. I picked a great time to be in my late 20s. Yeah, anyways, keep watching. I will hopefully make more content. No promises because everything's kind of in flux nowadays. But I do, enjoy those people who have stuck around, and I, thank you so much for all your supportive, kind comments. I really do appreciate it. And yeah, thank you so much.